Okay, welcome back, or welcome to the lab for Unit 2, Activity 2. We're only going to do one problem this time. And I'm going to assume, just for time's sake, that you've already familiarized yourself with the problem and have read everything. So this is just going to show you some quick answers, all right? Only one video, one problem. But that does have a lot of parts, so let's get going. So, part A for number three is talking about the United Nations and the fact that you start at 6 billion, but you're growing at 1.3% a year for an annual addition of 78 million people. So, there's a conflict there in the sense that, well, I think for, let's say a linear model, if I use U or blue, y is equal to mx plus b indicates an average rate of change or a constant average rate of change. In other words, if you were going to make, let's say, $2 an hour plus a dollar I gave you, notice every 2 hours, excuse me, every hour, you're just going to, if I work 3 hours, you put a three in here or a four in there or a five. So in other words, you're just adding two and another two and another two and another two. So you're having an extra addition of 78 million people in this example every time. So in this case, this indicates a linear, I don't know if I described that well, but that's describing a linear scenario. The only problem is in red here, as soon as you start talking about a constant percent change, then you're talking about an exponential scenario. So that's really the verbal. I know they asked you to, or I asked you to write it down, but the two descriptions are contradictory because one of them is describing a linear model, the other one is describing an exponential. And you can't have both. You have to choose one or the other. Part B is a little different in the sense that it's asking you to convert to billions or 78 million. Gosh, I think you read it like this to billions. So if you want to do that, you can cheat and just divide it by 1 billion, and you're going to get 0.078 billion. So if you, in other words, 0.078 billion is the same thing as 78 million. And if you wanted to do that, so if you're converting to billions, you could put that for your answer. And that's really important because the problem's also messed up in the fact that they're starting with an initial value of 6 billion, but then over here you're adding millions. So you always have to have the same units, especially if you're going to do a linear function. So let's go ahead and talking of a linear function and go ahead and get one. If I'm starting at, remember, I'm using y equals mx plus b here. And I know my increase is this much every year, 0.078. And they're both increasing both ways it was stated, but this time 0.078 times x. So it's increasing by 0.078 billion plus 6 billion. That was the starting value of the problem. Now in red here, if I want to do part D, remember if they want an exponential model, that looks like this. And I know that initial value is already 6. And the growth factor in that case, remember b is equal to 1 plus a r. If you can't see, you can always write it down. 1.3%, remember from up top, as a decimal is 0.013, or I think that's equal to 1.013. Okay, so there's your two models. Not too bad, huh? It's kind of quick once you start catching on here. Now, we could take the time, and let's go ahead and put the years from 1999. In 1999, that's times 0, so this is going to be 1 year later, 2 years later, 3 years later. Be careful because I'm always like I'm a year off here. You can't just say 10, but I think if you can even count on your fingers, 2002 was 3, 2003 was 4, 2004 was 5, 2005 is going to be 6, and if you keep going, that number there is going to be 11. And you could, if you wanted, take this 0 and plug it in to both the inputs to get the first values. 0 times 0.78x or 0.078x into the linear model would knock that out. 0 times anything, 0 plus 6, so that would be 6. And let me go ahead and write this in blue. And you could plug in 1 and you'd get 6.078. And you could keep plugging in values. Same thing for the red function. If I plug 0 into the exponent there, 1.013 to the 0, anything to the 0 is 1. So 1 times 6 would be 6. And you could keep plugging in the values successively the whole way. Let me show you a trick. Um, go ahead and I'm going to answer part E2 because we're going to make this table and see if we have the same prediction for 2 years. Okay. But if you go ahead to your calculator, and if you need to pause the video, go ahead. But I've gone already and plugged these in for time's sake. I'm going to show you a cool trick. So notice the blue is linear, red is exponential, and I kept those color coded the same here. Blue is linear and red is exponential. So I'm not going to fill them in. I'll let you fill them in. But if I go back to my calculator, and hopefully I talk long enough, if you got it out, plug those in, check this out. You have a table feature in your calculator. So all you have to do is hit second table setup. In my table, I think they had it start at time 0, right, which meant 1999. And then the table setup, that little triangle means the change in table. So the table is going to count by ones. And the independent and dependent just mean the auto feature. Calculator is going to automatically generate this table for you. So go ahead and check second table. And notice, and I don't have to plug in any of those numbers. I just have a quick read on both the linear and the exponential. Remember, this was the exponential outputs. And in blue, this was the linear. Cool, huh? And notice they're going up in very small, it seems very small increments, but we're talking billions here. So it's just, the problem is designed so that you'd have a really hard time graphing it. Because part E of your problem says, hey, they both cross here, but is there another time where they cross again? And if you're looking at your table, check out check out here, 6.54, 6.56, and over here, 6.46 and 6.48. So, and then over here, as you keep getting, progressively larger, those values cross again, 6.2 over even over here at 6.39. So let's keep looking, 6.3, 6.156, 6.157. Oh, where's the two values at? I'm trying to look right here, right in front of us. So there's two values there after year 0 and year 1. And so the real reason, if you could graph this, and I'm not going to try because it's really, really hard to do it on your calculator. It's set up to be hard so that you'd have to, use your table to really look what you're seeing. But my linear function, let's say that's increasing like this. Then my exponential function would increase. Now this is super zoom, okay? And what you're going to find is at time 0, that's going to be 0, 6, which is, if I can erase some of this stuff, that's right here, right? For both of them, they cross there, and they also cross here. So at 1, 6.078. And you could graph them. It's really hard to get that graph, but the real reason you have two values that are both identical is because it crosses in two spots. So that's the answer to that question. If you need to see it again, just go back. Okay, so I kind of talked you through part E. And gosh, which model predicts a larger population after the year 2000? So after the year 2000, if we're really looking, and we can go back to my calculator if you want, and I think my picture is now gone, but after the year 2000, you'll notice even in my picture, let's see if I can do that again. I'm sorry, I just went bye-bye. Oh gosh. So I had one like this. That's supposed to be a straight line, and something like this. So after they cross for the second time, notice that your exponential function is going to go, this thing's going to get higher much faster. So that's the thing that's going to win always. They'll say, in math terminology, means they'll say exponential functions dominate in the long run. So once they cross for that second time, they'll never cross again. And that's why this makes sense. You can say exponential functions always dominate. Okay, so which model? The exponential one. And you could say because exponential functions always dominate in the long run. Okay, so I hope that helped, and good job, and contact me with any questions as always. Take care.